acids and bases, I have a really funny video that I'll put on Learning, link to this. It's a song, and it helps remind you about the properties of acids and bases. It's called Acids and Bases Have Two Different Faces. It's really catchy, so I very much encourage you to watch it. So with acids and bases, we encounter these every day in our lives, okay? Like acids taste sour. So you've probably heard of citric acid before, right? All citrus fruits, really a lot of fruits have citric acid. Vinegar technically contains acetic acid, so that would be another type of acid that you might encounter in your life. Bases are also called alkalis. They are very slippery when you feel them. So cleaning solutions are usually highly basic, like ammonia. You guys heard of ammonia before? That is a base. And so also like bleach is also a base. Those kind of things. So if you ever feel something and it's slippery to the touch, then that means it's basic. Okay. So the first person to even come up with anything about acids and bases was this guy named Svante Arrhenius, where he said, based on electrolytes, that acids will produce hydrogen ions in aqueous solutions, and bases produce hydroxide ions in aqueous solutions. So we call this the Arrhenius concept, where acids have H+, and bases have hydroxide ions. And this was a very big step forward with acids and bases in chemistry. Now, this is a good stepping stone, but it didn't account for everything. If you look at this definition, then a lot of times people forgot about certain types of bases. So that's why it's not the best. So instead, we have the Bronsted-Lowry model, which allows for any kind of base, not just bases that contain hydroxides. And so this definition is more broad, where it says that an acid is a proton donor and a base is a proton acceptor. So a proton, we're going to talk about this all unit long. A proton is an H+ ion, a hydrogen ion. Okay, so acids, we learned this in Chem 1. When you look at a chemical formula, if it starts with an H, then you know it's an acid. And that's because the H is that proton that it will donate to something else. And then a base, whether it has hydroxide or not, will accept that proton for it. Okay, so that definition is really what we use more than anything else. So this is just an example of when we have hydrochloric acid dissolved in water. So the HCl is added to the water. And what happens is the HCl will donate or lose its H+ and give it over to the water molecule. And so we create this H3O with a +1 charge because the hydrogen had a +1 charge. And then it leaves the chloride with a -1 charge by itself. So that H3O+ that is created is called hydronium ion. And when in Chem 1, I usually don't use hydronium that much because it's just a little bit more. But I read that it is preferred for the AP exam that you use the H3O+ instead of just H+, but they still accept it. So if I ever mistakenly just use H+, it's because old habits die hard, and that's what I have learned when I learned it, and that's what I've been using. But they're interchangeable for the most part, okay? That hydronium or the H+. So when thinking about acids and bases, water, we know, is the universal solvent, and it is actually a very special thing besides just that. It's called an amphoretic substance, which means that it can act as either an acid or a base. It just depends on the situation, okay? So I have pictured here where if we would have two water molecules combine together or react together, then one of them, I don't really know which one, but one of them will donate the proton to the other, which creates the hydronium ion and then the hydroxide ion. And so whichever one does the donating, that would be the acid. Whichever one accepts it, that would be the base. But that's just what amphoretic means, is that it can be either an acid or a base. Just depends on the situation. So when we have this situation, then this leads us to equilibrium, because theoretically we know that pure water doesn't have a charge, but maybe if there's this transfer of protons, something's happening here. And so Kw is very similar to like our KSP or our Ks that we had in Unit 7. It's called the ion product constant. W, I think, is supposed to be for water, okay? Where when you multiply the concentration of the hydronium ion times the hydroxide ion, then we get this value for Kw at 25 degrees Celsius, which is 1.0 times 10 to the negative 14. So that's just a constant. It is on the AP equation sheet. And so if we were to know that the the Kw is equal to that value, then at 25 degrees Celsius, the concentrations of the H plus or the hydronium and the hydroxide are both equal to 1 times 10 to the negative 7 molar. So this is just the constant that we get for this. So when we have the Kw and we know the concentrations of our hydrogen ion or our hydronium ion and our hydroxide ion, then we can figure out if a solution would be neutral or acidic or basic. And so it all depends upon how are they related. So if they're equal, then it's neutral. One's not overcoming the other. If it's going to be acidic, then the H plus is going to be greater, or the hydronium will be greater. And if it is basic, then the hydroxide will be greater. So I think I left space for you to do your greater than or equal to signs, kind of thing. But just know that for each case, this is an equation that we can use to solve for the other one. Okay, especially if you knew what the hydroxide concentration was, then you can plug in here and solve for the H plus or the hydronium concentration. Okay, but it is important to note that this is temperature dependent, like everything else that we had in Unit 7. So 25 degrees Celsius is usually what we'll have, but the Kw could be a different value if it was at a different temperature. I will not try to trick you that way, but it's just important to know that. So, and we'll get more into pH in a little bit too. So the pH could also deviate as well, which actually happens a lot in this classroom because it's colder than 25 degrees Celsius normally in this classroom. Side note, struggle of my teaching career. Okay, so when the hydronium ion concentration or the H plus concentration in aqueous solution is typically small, then this gives us the pH scale. You guys have all heard of pH before, right? Nothing new. Okay, so the pH scale is a log scale based on 10, where the pH is equal to the negative of the log of the hydronium ion concentration. So that's one thing everybody forgets at first is that negative. That just means that if you take the log of whatever number you have, it'll be a negative number. So just make it positive, okay? That's why it has that negative in the equation. So for a solution, when the hydronium ion concentration is 1 times 10 to negative 7, then that gives us that the pH will be 7. Okay. Now, this one is tricky for people. Rounding to significant figures with logarithms. So remember, on the AP exam, sig figs are nice because you don't want to lose points because of them. But even if you get all your sig figs wrong, on a free response question, you would only get maximum -1 point, no matter what. Even if you do them all wrong. In order to figure out the significant figures with a logarithm, the number of decimal places in the log is equal to the number of sig figs on your answer or on the original number. So, for example, if we had the H plus concentration is 1.0 times 10 to the negative 9, that 1.0 is two significant figures in the original, in what we would put into the log function. So then those two significant figures tell us we have to have 2 decimals on the end. A lot of times it'll work out that you will just have 2 decimals on pH, but it's all due to the fact that it's the number of sig figs going into the log function gives you the number of decimals when you take it out. Okay. A lot of times it is 2, but don't always just rely on it. Okay. Some other similar skills, yeah.
So whenever the concentration equals to 1.0 times something, the exponent is that usually the pH.
Yeah. If it's 1, yeah. Yeah. It's a quick way to solve it. Yeah, that's a good thing to see. I think. I don't think it is. Okay. Something else we have is called POH because we have concentrations of hydroxide ions. So we also have the POH, but it's different than pH. Usually we want to report things in pH, not POH. So if you were to find the POH of something, then if you add the pH plus the POH, it should equal 14. So that would be a way for you to switch it if you need to in a problem. And also, we're going to talk more later on about something that's called pKa. But pK, this P is just the significance that this shows us that whatever we're doing to whatever after the P, it's a negative log of that number. Okay? So, like if it's POH, we get the negative log of the OH. If it's PK, we're going to take the negative log of the K. Okay? So that's what that P notation is for on value. Okay, so when pH is neutral, neutral pH is what value? 7. Yeah. pH is neutral at 7. So the pKw, if you were to find that, it would be 14. And so then the pH and the POH would be equal to 7. So those are just some more numbers with that. And last but not least, because people always forget about this, I don't know if you do this or not in math class, but it's important to know, if you have to take the inverse of the log, what you do is it's on your calculator, it's 10 to the x power, okay? And so sometimes we might know the pH, but we have to know the concentration of the hydronium ion. So you would take 10 to the negative pH power, and then that would give you the concentration. Okay, it's just the inverse, and I'm pretty sure if you look on your calculator, it should be like the second function of the log button. You might see that up there, like 10 to the x. And so you just have to be careful. Don't forget, a lot of times people will like try to divide by log, and that's not a thing. You have to do that special function to get there. Okay. We will do this after the AP exam and a lab where we have done an acid-base reaction this year, but we did not use a pH meter. So a pH meter can tell us actually, as you're mixing chemicals together, how does the pH value change? So you can see where it is at starting point, and then you can see how does it change over time. And so we can also just read whatever a pH value is for an unknown pH system. So we'll use those after the exam one at a time. Okay, so I've got 2 examples that they're practicing using these equations. Okay, so let's just do example 1, and then we'll call it, because I think we get out of here in about 6 minutes, I think. Okay, so we want to find the pH and the POH for each of these things. Or would you guys rather do 2, or would you rather do 1? Which one's harder? Maybe 2 would be better. Because don't you just plug it? Yeah, you just. Yeah, let's do 2. I like it. Let's speed up this process. Okay. So the pH for a sample of human blood was measured to be 7.41 at 21 degrees Celsius. So from this value, the 7.41 is our pH value. We need to find the POH, the hydroxide or the hydronium concentration, and the hydroxide concentration for the sample. Okay. Personally, there's lots of different, there's many paths to get to the same answer here, but what I like to do is, if I can, I like to use the pH plus the POH equals 14. Because it's just so much easier for me if I use this equation. So that's what I would use to first find the POH. Okay, so the POH, we would take the 14 And now, keeping significant figures, when subtracting, you have to keep decimal places. So I'm going to write 14.00. Since my pH is 2 decimals, that's 2 decimals. I'll keep 2 decimals on my answer. Okay? So 14 minus 7.41. That's 6.59. Okay, thank you. Okay, so that's easy. That's nice. Right? That is the pOH. That's the first answer. Okay. Now, we can let's just keep going with this number that we just got. Okay. So now that we know the pOH, we can find the hydroxide concentration using that answer log equation, where for the hydroxide concentration is equal to 10 to the negative pOH. So I need to take 10 to the negative 6.59. So if you have a graphing calculator, I'm pretty sure that you can just hit the second log and then negative 6.59. If you have to use my calculator, you have to put in an opposite of that. Ooh. But, so now, this is like a backwards of significant figures. Did we get like a bunch of zeros and then 257? Anybody that did it? Yes, I think that's what I got. Yes. Okay. So now for rounding, right, with this whole thing, the decimal places on the pH or the pOH tell you the number of significant figures that you round to when you use your log button. Okay. So since our pOH had 2 decimal places, we should just round our answer to 2 significant figures. So instead of 2.57, just say 2.6. Okay. 2.6 times 10 to the negative 7. And then concentration, what's the unit on concentration? Molarity. Yep. So that's the hydroxide. It's the number of decimal places on a P number tell you the number of full sig figs when you use the log. Yep. And then the OH, to go to the H3O plus, you could do 2 different ways. You could use the KW equation, or you could do the anti-log of the 7.41. Either way, if you want to see something different, like the H plus or the H3O plus is equal to the KW divided by the hydroxide. Maybe you see that way. So then 1.0 times 10 to the negative 14 divided by 2.6 times 10 to the negative 7. .8 times 10. 3, 4, 5, 6, 7, 8 times 10 to the negative 8. More. Okay, so tomorrow we'll start class. I know it's really quick, but tomorrow we'll start class and we'll look at all of the possible equations you can use, because as long as you understand how to use those equations, you'll be fine. Okay?